Welcome. This video is about file I/O. This gives me an opportunity to talk about the read and write traits and the other ways in which Rust treats I/O not only for files but also for other streams in an idiomatic fashion. We start with looking at an example. The typical stuff for file I/O is located in the FS module and the I/O module. FS is everything to deal with files, like opening and closing files, and I/O is all about reading and writing. Here I import the FS module as such, the file type, and I import the read, write, seek, and seek from traits. We'll see in this file what we need. I want to begin with a convenience method, namely fs write, which allows me to write an arbitrary byte sequence into a file. This gives me an opportunity to talk about error handling. If I would just remove this unwrap here and let x equal this here, then the type of x is always result something error. Basically all I/O functions follow this pattern, that they have the result enum with the first argument something. Here it's just empty, and the second an error. If you go to the library and see what the write function does, then you see that it returns an I/O result in this type, in this case templated with an empty type. And if you look what that is, you see that the I/O module defines a result macro template, which is just a normal result template with a type given and error as second argument. That's a general pattern. So therefore, in this case, I'm not really interested in the error handling, so I am lazy and I just do unwrap, get rid of the error because I know it will go well, and that means I have written the file in this way. This creates a file called file.txt in the current directory and writes these 26 letters in there. Then I read it back, again with a convenience method in the fs module. You can just say read to string. Now this returns something else. It returns a result whose first argument is a string, first template argument. By assuming that this works, I can just unwrap and remove the error case, and then I get a string out. So these are two easy functions to write a byte sequence to a file or read data into a string. Now the string must be UTF-8 data, so if it's not UTF-8 data in the file, then this here will actually return an error. But let's look at the next case where we use the more low-level functions. This is basically the lowest level thing. I use the file type from the FS module and create a file that's creating a new file on disk with this name. Obviously this can fail, and again I get an error, but if I unpack that, I get a thing of type file. Since I want to write to this file, I make it mutable. Now, the write thing is essentially the main function, the main method in the write trait, because the type file implements the write trait. I can just call write here. If you look into this here, you're going to get a size I/O result. That is, we give a slice, a byte slice in, which is the data to be written, and I get a size out if things go well. Now, this follows the same semantics as the write system call in Linux. That is, if things go well, it might only write a part of the data. In most cases for file I/O, it will write the whole block, but you have to look at the size and check whether it has written the whole buffer. There's other functions. If we go to the write trait, where you can do other operations. Let me just have a quick look. If I go to the library and look at the public trait write, that's all the documentation there. And let's just have a quick look. You have the write function, which is what I just said. Then you have a write vector, where you can give a list or slice of buffers. Then you have flush, which we will see in a second. Then you have write all. That guarantees that either it writes the whole buffer or it returns an error. And then you have write all vectored, write format by giving a format string, and a few more special methods, which you can always look what you want. And we are already through to the seek trait, which we will look at in a second. It's important that the file type, when it's dropped, automatically closes the file. So this flush would technically not be necessary to write the file successfully. Once this scope here is left, this variable is dropped, and then the file would be automatically closed, and that's it. But you can no longer handle errors there. That is, if you want to make sure that the data is actually written and you handle errors, then you have to call the flush method, which has no arguments and returns either nothing or an error. So therefore you can catch errors here. If you do that and then it goes out of scope, you know that the file is successfully written. Let's first see these things in action. So we have written the file, we have read the data back, we have wrote 26 bytes, and then some more, which we will look at in a second. Let's quickly look at the rest of the program. Here you see the other direction. I open a file, I give an array of 1024 bytes, and then I do a read call. Again, it's possible that it reads less than this buffer, but that's the upper limit. And then I can look at what size it read. And the last example is a seek. I can seek in an open file and just seek either from the start or from the end or whatever, or relative, and then I use the same method. So that's your basic low-level I/O. Here I see that I wrote 26 bytes, I read it again, I see the data, and here after the seek I just read the last 13 bytes. Let's look at buffered I/O. For buffered I/O we have the buffRead trait and the buffReader class or struct and the buffWriter struct. So let's quickly go through it. When I have an open file for writing, like this here, then I can wrap it with a buffWriter. Here I can give the capacity, and I stick this F into the buffWriter. Note that this is moved into the writer, so I have no longer access to the file F from after this call here. Here I write this byte stream one by one with the write method, but I use the method on the buffWriter. So this then goes first in the buffer and will only be actually written when the buffer is full or when I flush it. Other than that, it's exactly the same as for unbuffered I/O. Reading is the same. I take an open file for reading, I wrap it into a buffer, and here I just want to read it into a vector of bytes. So I read one by one by having a little buffer here of 1 byte only. I read from the buffer, from the buff reader, and I know that if I read 0 length, then the file is fully read. And here I push the byte into the buffer. It's not the most efficient way, but with buffered I/O it's better than nothing. Let's see how this works. Yes, it writes 28 bytes. Let me finish by showing you standard in and something else the buffRead can do. The buffRead trait, among other things, has a function called readLine. That basically just fetches a single line from the buffered I/O. You give a mutable string, and the data being read is appended to the string. Therefore, I clear the string here and append to it here, because I want to read the file which I just wrote line by line. Once I get something back with size 0, I know that the file is done. I'm using the standard in here. That is, I call the standard in method from I/O, which gives me an object representing standard in, but I still have to lock it well, in this case I wouldn't, because I use only a single thread, but in general I am supposed to lock this thing to get a so-called standard in lock, and this implements the trait buff read on standard in. So that's a very convenient way to read from standard in line by line. So let me see that. So I hit ABC, D, E, F, and as you can see, I get the line with its line end back, and the moment I close the file, I'm finished. There would be lots more I could tell you about I/O and file I/O, but for this video I'm content with having shown you the basic functionality of the read and write traits and of the buff read trait. You can just look through the library or follow the links in the accompanying web page to find out everything you can do. I hope this was fine and gets you started with file I/O and other I/O in Rust. See you in the next one.